major implication and mean analysis. My name is Femi, a PhD student in the Department of Mathematical Sciences, Indiana University, Indianapolis. Okay, in our previous video, we checked measurable sets. Then we are able to define what a sigma algebra is and the basic properties of sigma algebra. Then we talk about measurable space, and then we define Borel subset of R, whereby we also define the smallest sigma algebra, which is an Borel sigma algebra that can be generated by some set of R. So the next thing we need to check is our measurable functions. Now that we are done with the measurable spaces, which is an order pair of a set X and the sigma algebra on X. So today we tried to check what a measurable functions are, but before then we like to do a quick revision on inverse image. Definition, inverse image. Okay, so if a function f a map x to y is a function and then A is subset of y, then the set f inverse is defined by f inverse of A, which is equal to x belongs to x, shows that f of x belongs to A. So we have that as our definition. So if I'm going to get something like this, we have something like this, and we have a function probably like this, and then this is our x, this is our y, and this is our x. So we have a subset of A here, and this is our A, but not necessarily in a sequence like that. Then the inverse of this A is that actually goes to some point in our x. Okay, so that is just the ideology. So let's take some example. Inverse images. So suppose our function f and we have our domain to be 0, 4 pi, and it mapped to R and is defined by f of x equals to sine x. And then the pre-image of 0, infinity, that is all x, such that sin x will give us this result. Another one, the inverse of 0, infinity, or we can just say we are going to go by our definition. This will give us the values of x that belong to 0, 4 pi, such that sin x is equals to 0, infinity. And I want x equals to inverse of 0, infinity. So if you take the inverse of that guy, then you're going to have 0, pi union 2 pi, 3 pi. So if you find the inverse of close interval 0, 1, the same thing as you taking the inverse of close interval 0, 1, and that is equal to 0, pi union 2 pi, 3 pi union 4 pi. Okay, so an example, inverse of -1, since I'm taking this inverse of sin 1, that's equals to 3 pi over 2, 7 pi over 2, and then the inverse of 2, 3, that is empty because our sin x only oscillates. We have this, so we have this as our sin x. So we have 1, and then we have -1 here. Then we have our sin x to oscillate between this point. So we have something like this, and that's so we don't have any codomain that contain 2 or 3, so that's absolutely empty. So you can also verify that. So another definition that will lead us to start defining the measurable function is some basic properties of inverse images. So suppose f shows that x tends to y is a function, and then this property shows the inverse of y take away a equals to x inverse of a for every a subset of x, and b the inverse of the union of a belongs to curly a is equals to the union of a belongs to curly a f inverse of a, and so for every set of the a of subset of y. Then for the intersection also, the same thing holds, intersection a belongs to a f inverse of a for every set called a subset of a. So let's prove that. So suppose A subset of Y. So for every x that belongs to x, we have x belongs to f inverse of I take away A, and this is equivalent to f of x belongs to y take away A, and this is equivalent to f of x does not belong to A, and this is equivalent to x does not belong to f inverse of A, and this also equivalent to s belongs to x take away f inverse of A. So let's prove B now. So suppose our fancy A is a set of subsets of Y, and then what? Then X is an element of F inverse of U, and belong to fancy A is equivalent to F of X belong to union A belongs to fancy A, and this is equals to F of X belongs to A for some A that belong to fancy A, and this is equivalent to X belong to F inverse of A for some A that belong to fancy A, and this is equivalent to X belongs to the union of A that belongs to A, F inverse of A. So similarly, you can also prove for the second part, for the about part C, proof of C. So you can also follow the same procedure. So the next definitions: inverse image of a composition. Suppose function f x takes to y and g y maps to w are functions, and then g composite inverse of these of A is equals to f inverse g inverse of A for every is set of W. So let's prove this. Suppose A is subset of W. So for x that belongs to X, we have x belongs to G composite f inverse of A is equivalent to G composite f of x belongs to A, and this is equivalent to G of f of x which belongs to A, and this is equivalent to f of x belongs to G inverse of A, and this is equivalent to x belongs to f of inverse G inverse of A. Okay, so now we can now define what a measurable function is. In definition, measurable function. So suppose S comma S is a measurable space. So a function f such that x maps to R is called x measurable. If f inverse of B, f the inverse of Borel set belongs to sigma algebra X. For every Borel set B subset of R. So we have that as our definition, that is the pre-image of Borel sets must take sets that are in the sigma algebra X on X. So let's check some example. Example of measurable function. So one, if our sigma algebra is only empty set on X, the full set X, then the only measurable function functions from X to R and the constant function. So that is, if we have X this, then this our X, X is our R. So for us to find the function that either take the full set of this or is empty, then that function must be a constant function. Something like that. So or else it takes an empty set, or say it is empty. So next example, B, if X is the set of all subsets of X, this is part. Okay, B, we have if X is the set of all subsets of X, so then every functions from, because that with the power set, then every function from X to R is X measurable function, because our sigma X not contain the whole set. So example C, if X is a specific sigma algebra, have an empty set. infinity and r, which is a sigma algebra on R. So then a function f such that our map R is x measurable if and only if f is constant and infinity, 0 and f is constant 0, infinity. So you can check something like this. So we have 0, minus 1, minus 2, minus 3 to the dots, 1, 2, 3, 10 dots. So you can have a function of this form. So from 0 down here, you can have like a constant. So let's map like this point. We have this here arm. This here arm. So then you can have something like this. So let me change this color. Alright, so you can have something like that. So then let's define a specific function called characteristics function. Definition: characteristics function. So we denote it as chi in. So suppose E is a subset of a set EX. So the characteristics function of E is the function chi E such that X mapped to R defined by chi E of X equals to 1 if X belongs to E and 0 if X does not belong to E. So something like this. So F0, F1, F our X, then we have our chi E of X. So then we have our from this point to this point to be our E. Here we have something like this. Here we have 0. We have a jump down here to 1. Here we have jump here down 0. So that's our characteristic function. So example, inverse image with respect to a characteristics function. So suppose we have a measurable space and is subset of X and B is subset of R, and then the pre-image of a characteristic function will be equals to, so the possible pre-image we are going to have is E, is this E. We can also have X take away E. Okay, we can also have the full set X and can also have empty. So our pre-image will only be E if 0 does not belong, if 0 does not belong to B and 1 belongs to B. We are going to only have the complement if 0 belongs to B and 1 does not belong to B. And we are going to have the full set if 0 belongs to B and 1 belongs to B. But it will be empty if 0 does not belong to B and 1 does not belong to B. So you can take your time to verify that. So then we see that our characteristics function will only be an X measurable function if and only if E is an element of our sigma algebra X and X. Alright, there's another better way to define the condition for measurable function. Condition for measurable function. We are suppose we have a measurable space and we have our function f x to r is a function such that the pre-image of a to infinity is a sigma algebra. Is for all a that belongs to R, then f is X measurable. So if we can prove this, then we can also use these conditions to check if our function is X measurable. So let's go straight to the proof. So let T equals to A subset of R such that the pre-image of A known as sigma algebra. So we want to show that every Borel subset of R is in T. So we want to show that every Borel subset of R is in T. So to do this, we have to first show that T is a sigma algebra on R. Then we can now build T by making use of our open set. So first show that T is a sigma algebra on R. So let's show that. And don't forget, a sigma algebra means that it contains empty set, is closed under complement, and then is closed under countable union. So first, empty set belongs to T. So we claim that. Why? Because F inverse of empty set, that's equals to empty set, and that belongs to X. If it belongs to X, then it is in T. Okay, so 2, if A belongs to T, then F inverse of A belongs to X. And then we know that if the pre-image of A is in X, then the complement also should be in sigma algebra. And by the properties of pre-image, this is the same thing as F inverse of R, take away A. And that shows that our T is closed under complement. So thus, our take away A is also in T. And in other words, T is closed under complementation. So the last is the countable union. So 3, if A1, A2, that belongs to T, then the inverse of A1, inverse of A2, that also belongs to X. So, and we know that if F inverse of K belongs to this, then the countable union also should belong to this. And then this is the same thing as F inverse of K corresponds to infinity AK. So thus countable union of AK belongs to T, and this implies that T is closed under countable unions. So since these three conditions are satisfied, that shows that T is a sigma algebra on R. T is a sigma algebra on R. And if that is true, then by our hypothesis, have T contains a comma infinity such that A belongs to R. So since T is a sigma algebra on R, so since T is closed under complementation rather, then T also contain this minus infinity comma A. Next will be the B, and B belongs to R. And because sigma algebra is also closed under finite intersection, so what we are just trying to do is just to build a Borel sigma algebra. So because T is closed under finite intersections, so if we take the intersection of these two guys, so we have we see that T also contains A comma B, such that A comma B belongs to R. Okay, and then because we can write our open interval as countable union, our open set as countable union of open interval, and then minus infinity comma B, also write it as UK equals to 1 to infinity minus K comma B minus 1 over K. So and T is closed under countable unions as part of the properties of sigma algebras. So we can conclude that T contains every open subset of R. So that's the sigma algebra. Contains the smallest sigma algebra on R that contains all open subset of R. So those f, x, and x measurable. So that means that if we can get a set whereby we can actually use it to build a sigma algebra on R, a smaller sigma algebra on R, that means that we can use short sets to define if when a function is x measurable. Okay, so we can now define another measurable function which we call Borel measurable function. Definition: Borel measurable function Please suppose our set X now is not subset of R. So a function f map X to R is called Borel measurable. If the inverse, the pre-image of B is a Borel set for every Borel set B subset of R. Okay. Then let's prove this theorem. Then from that we can continue in the next video. So now this video will not be too long. So you see, every continuous function is Borel measurable. So let's prove this. Okay. Proof. Suppose S is subset of R is a Borel set, and then we have our function map X to R is continuous. So to prove that f is Borel measurable on R, Borel measurable, so we fix A to be an element of R. So if X belongs to X and then our f of X is greater than A, so by definition, then by the definition of continuity of f, so we can find a small delta greater than 0 such that f of y is to be greater than A is for all y that belong to the neighborhood of X. Section X. Thus, the pre-image of A comma infinity is equals to union of X, whereby f of X, where the pre-image of A of this, and then the neighborhood intersection X. This intersection our X. So the union inside our parameters above is an open subset of R, and its intersection with X is Borel set. Thus we conclude that f inverse of A comma infinity is Borel set. Notice this guy is open subset of R, which is a Borel set. And then our X is also Borel set. So intersections or the countable union of this Borel set will still give us the countable union of this Borel set. will still give us Borel set, and the intersection with a Borel set will still give us a Borel set. So since the pre-image is Borel set, then F is Borel measurable, and that implies that every continuous function is Borel measurable. So hope to see you in the next video, where we check some likely theorem related to this Borel measurable function. Thank you.